right, thank you. Thanks for coming to my talk on principal type inference in a Boolean algebra of structural types. The slides are online. The slides are online if you want to follow along at your own pace. It's in the event page. Okay, so what are we going to talk about today? We're going to talk about subtyping, structural types, ML-style type inference in the context of MLstruct. So MLstruct is a core language for the programming language that we are developing in my research group at the Hong Kong University of Science and Technology. And the basic idea of this language is to look at TypeScript and realize that there's a lot of good stuff in there. Okay, TypeScript is one of the most popular programming languages these days. And so surely there's some good ideas and useful ideas in there. And so we want to reuse adopt these ideas, but in a context where, in a sound type system context, okay? Because TypeScript has a lot of sources of unsoundness, fundamental unsoundness, right? So we want to take these structural typing ideas, make them sound, and additionally, TypeScript is not very functional. It doesn't have great type inference, so we want to solve that, right? So let's solve these problems. The features of MLstruct are subtyping, fundamentally, and structural types. And the idea of structural types is that the types, you can compare types based on the structure instead of purely based on their names and pre-declarations. And then we have class hierarchies with single inheritance, which is actually important, as we will see. We have pattern matching, which can be open in the sense that you are not forced to specify a fixed set of data types that you want to make part of your data structures that you are matching. So it's a form of extensible pattern matching. And finally, we have recursive types and equirecursive types in particular, just like in TypeScript, where you can refer to a type in its own definition without having to use any fold and unfold primitives at the term level. Finally, we want principal type inference. Okay, so this is a pretty strong property. It says that whenever the compiler infers a type for your expression, which doesn't contain any type annotation, this type happens to be the most general that you can assign to the corresponding expression. So if you can assign any other type to the expression, the inferred type will be at least as general as that other type, right? So let's see how we can do this. So first we look at a few classical TypeScript features, such as singleton types. So in TypeScript, 0 is not just a term, but it's also a type. It's a type of specifically the constant 0, and it's a subtype of nat, right? So TypeScript doesn't have nat, but we have nat in our language. And then we have record types, which have fields, and they are related by subtyping through width and depth subtyping. Width subtyping allows you to drop some fields from record types, and depth subtyping allows you to widen the types of the given fields. And importantly, we have these union and intersection types. So they are basically the join and meet of the subtyping lattice. Okay, so we also call them least upper bound and greatest lower bound. And we will see that they're actually fundamental in the idea of structural types. And here's an example of a union type. So 0, the type of the value 0, is actually a subtype of the type 0 or 1, which is a union type representing either the value 0 or the value 1. And this type is a subtype of nat because both sides are subtypes of nat. Okay, and nat itself is a subtype of int. So let's look in particular at the class declaration for a person which has two fields, name and age. Okay, we can instantiate this class using a term constructor because the class introduces both a type constructor and a term constructor. And we can define functions such as isMajor that rely on the field age. So in this case, isMajor has an inferred type that says the argument should be a record with a single field age of type int. And we can call isMajor on a person P that we have created before because this works because person has the right structure, right? So the person type is a subtype of the body of the class, which is this record type with two fields in this case, which is itself is a subtype of the record type that we're asking for, which contains an age field, right? And so this just works out naturally. You don't need any special handling. You don't need any special row variables or things like that. And so if you recall, person is defined this way, and we have the following subtyping. The person type is a subtype of its body, but we don't have the other way around. And this is very important. In TypeScript, person is equivalent to its body, and that's actually one of the sources of unsoundness. In MLscript, this is not the case, and that means there's a notion of nominal typing in addition to the base structural typing of our type definitions. Okay, so how does it do this? Well, it uses the notion of nominal tags. So each class has an associated nominal tag, which is represented by the pound sign followed by the class name. And this type, this nominal tag, represents the nominal identity of the class. So actually, the person type can be expanded into an intersection of its structural components, which includes this nominal tag. And that's why we cannot use a record as a person if it doesn't have this intersected nominal tag. Moreover, multi-field record types are actually desugared themselves into single field record types that are intersected. And so the basic idea is that we look at the complex types defined by the users and used by the users, and we decompose them into basic structural components, which is actually one of the key ideas to make type inference and constraint solving manageable and easy to do. So let's look at another example where we define the classical either data structure, which is either an instance of the left case or the right case, where here left and right are defined as normal classes with a value field. And so we have seen intersections. Now let's talk about unions. So unions come up naturally. They are introduced by the control flow of the program. So for example, if you have some branching expression where one branch returns an instance of left and the other an instance of right, then what you get as a result is a union of left and right. Okay, so that's how unions are introduced. And in this particular case, since we defined either in this way, the corresponding type is a subtype of either. And so given a value of this union type, you can use it by selecting the value field on X, okay, which yields the type 42 or true, because both sides of the union have a value field, so you can perform this field selection. But that's not necessarily what you want to do here, because it kind of merges the two values and you lose the information about where the values came from. So what you can do to handle both cases separately is to do pattern matching. And in MLstruct, we pattern match on classes. So pattern matching works with class patterns, so class names basically on the left of the arrows. And so the pattern matching construct refines the type of the scrutiny that is being pattern matched, X here. So that's in this case, we know that X is an instance of left. So we know that the value field here refers specifically to the value of the left case. Okay, so that's why here we know that value is an int, and we can add it to 1. But in the right case, x.value is a Boolean, which is why we can use it in an evenness expression. And so what we get as a result is y of type int. But in this particular case, we could actually have done it a bit differently. We could in fact still select the value field on the original x value. And since both int and bool happen to be classes in MLstruct, you can also pattern match on them, right? So in this particular case, you can also do things this way, but that's not always the case. If it happens that the left and right instances store things that are not classes, for example, records or functions, you cannot pattern match on records and functions. So in that case, you would have to pattern match on the proper left and right classes. Okay, so far so good. Any questions? Yeah.
So you said that classes are nominal, right? But you also showed that 0 was actually a subtype of net.
Yes, yes. Oh, so classes are nominal, but you have class hierarchies, right? Single inheritance class hierarchies. So basically, 0 is can be seen as a class that is a subclass of nat, and nat is a subclass of int, right? So basically, a subclass contains all the nominal tags of its parents, right? Intersected together. Okay, so actually, pattern matching becomes more interesting if you start introducing default cases, because now it's no longer completely clear what the type of a function that does pattern matching with default cases should be. So here is a function that pattern matches on its parameter x and handles the left case, and it also handles any other case, in which case it returns the parameter unchanged. So what should be the type of this function? I'll give you just 1 minute to think about this, right? So x could be left, right? And it could be anything else. So maybe a first guess would be that the argument should be left of int, because we are adding the value here. Or alpha, where alpha is left unspecified, right? A type variable. Any problem with this approach? Does anyone see a problem with this approach? Yeah.
Don't the two sides overlap and then?
Exactly. Yeah. So you can see that very easily by instantiating alpha to top, for example, right? So if you instantiate alpha to top, which you can always do because this is a polymorphic type, right? So you can always take it and instantiate it. You get a function type which is just top to top, which lets you call the function with a value of left that has the wrong type inside. Okay, so this left of true will pattern match in the first case because it's a left instance, and then it will try to add true to 1. So that doesn't work, right? This is not the right type for f. What we really want to express here is the idea of removing the left constructor from the type variable alpha. Okay, so how can we express this idea? It turns out we can use negation types in this case, and nominal tags. So we can desugar this pseudo type, which is type tau, from which we have removed the constructor, by an intersection of the original type and the negated nominal tag. Okay, and so the above signature is just syntax sugar for this signature. And so whenever you have a nominal tag of two unrelated classes, the one is always a subtype of the negation of the other, right? Because if you have an instance of one of the class, surely it's not an instance of the other class. And equivalently, you can say that if you take the intersection of the two unrelated nominal tags, you get bottom, because there are no values that inhabit this intersection. Okay, and this relies on the single inheritance assumption, of course, because if we had multiple inheritance, then there could be classes that inherit from both left and right, and this whole reasoning wouldn't work. So this kind of raises the question, what specifically, what do these types mean, the intersection, union, negation? And so a natural way of thinking about them is as a natural way of thinking about types is as sets of values. And then you can say maybe union and intersections can be understood as the unions and intersections of the corresponding sets of values. But actually, this doesn't work so well for type inference. It doesn't really scale very well to polymorphism in particular. So we refrain from doing this. But to make sure that these connectives, union, intersection, and negation, are still well behaved and behave intuitively, we make sure that they form a Boolean algebra. And so that means that we have the usual rules of distributivity, the Morgan's laws, negation, complementation, and all of these rules that we are already used to, so that these things behave naturally. Okay, and so here's another example with recursion this time. So we are defining a list data structure as a type synonym. We're saying that a list of A is either an empty list, nil, okay, which is a class with no data inside, it's just a marker class, or a cons whose head is an A, or and whose tail is a list of A. Okay, so there's the recursion here, and cons here is a precisely typed cons cell. So the types are equirecursive, as I mentioned. You don't need any fold and unfold operations, and that means that you have all sorts of natural and very useful subtyping relationships between different variations of these types. For example, you can take the cons of some type tau and a list of pi, and this happens to be a subtype of a list of tau or pi, which makes sense. You can also precisely type things like tuples. Using just this list definitions, you can represent tuples of 3 elements by representing them as cons of nil, right? You can also represent lists of at least 2 elements or lists of or non-empty lists, right? And this all comes kind of for free in the sense that you don't have to apply any coercions between these different types. They're all related by subtyping in a natural way, okay? And so here's an example of using this list data structure where we define the classical list sum function, recursive function. And this is the type that MLstruct infers in this case. MLstruct doesn't actually care about our list type definition because all its type inference is done structurally. So what it says here is that the type of sum is for all alpha to int, where alpha is upper bounded by an expression, a type expression that refers to alpha itself. So this is like a recursive bound, and it happens to match with the list definition that we have. So we can actually ask MLstruct to make sure that this sum implementation conforms to the signature that we may want to provide. Okay, so this structure basically matches the list structure, the list recursive type. Okay, so how do we do type inference in this language? Well, the main difficulty in type inference here is constraint solving. Okay, the actual type inference rules are pretty straightforward. And so when you solve subtyping constraints, you have easy cases that you can handle, such as subtyping recurs with the same fields, in which case you just constrain the corresponding field types, and subtyping function types, and subtyping intersections on the left, and unions on the right, where the left-hand side happens to contain a nominal tag that's a subclass of a nominal tag that's also on the right-hand side, in which case you are done. And so here we have equivalences between these two, the original constraint and the simplified constraint. And this is important for principal type inference, right? We want to have really an equivalence between these two constraints, otherwise we would lose principality. And so another easy case is when you have a union on the left, which is the same as decomposing the constraint into 2 sub-constraints, or an intersection on the right, similarly. And finally, we do transitive closure on the type variable bounds, and we record the bounds that we encounter on type variables. So if we have type variable alpha, which is constrained to be a subtype of tau, then tau becomes an upper bound of alpha. And we constrain all the existing lower bounds on alpha to be less than tau to make sure that they are consistent, right? Because one of the main points of constraint solving is making sure that the resulting type schemes are consistent. And so there are some problems. There are some ambiguities due to structural types and unions in particular, and also intersections. For example, what do you do if on the left-hand side you have a record with several fields, and on the right-hand side you have a union of possible records? So here it's not clear what to do. You could constrain tau to be less than tau prime, and that would be sufficient, but it's not necessary. You could also constrain pi to be less than pi prime. And in the general case, you cannot know locally which one to constrain, and you would have to perform backtracking, and you would lose principal types, because as soon as you start just trying things out, you have to enumerate a set of possible type solutions, and this doesn't scale, and it doesn't allow you to have principal types. Another problem is when you have type variables involved in these unions and intersections in wrong positions. And so how do we solve these problems? Well, the first idea is to bend the types to our will. So we add structure to the lattice of types in order to make these kind of things simpler to handle. So as a first observation, we see that unions of record types are actually not very useful in the language. The language allows you to pattern match on classes, but it doesn't actually let you distinguish the components of a union of records, right? So you cannot do anything useful with such a union of records which don't share any fields. Okay, so in this case, we can say, then let's consider that it's the same as top. Okay, so we had the subtyping rule that top is less than this union of records with unrelated fields, and that makes top equivalent to that type. Okay, and we have similar ideas for unions of records and functions, and also for intersections of functions and unions of functions. We add a lot of rules that do not necessarily hold in all languages. In particular, these rules do not hold in the set theoretic interpretation of types, okay? But they hold in our Boolean algebra. And the main consequence is that union and intersection types no longer directly denote the intersection and the union of their sets of values, right? So the set of values of a union type is actually now an over-approximation of the set of values of the corresponding type components. And this is fine, as long as it doesn't break subtyping, right? If this allowed us to say that top is less than a record type, for example, of course, that would be bad because it would break the program. It would allow programs to crash, okay? So as long as we don't, as long as these new subtyping relationships do not lead to bad subtypings, in a sense, like relating the wrong constructors together, then we are fine. And this is actually more tricky than it seems. You have to be very careful when you do these kind of things. For example, you couldn't say that the intersection of a record type and a function type is bottom, even though there are no values of these types in the language. If you say that, then actually it breaks because of distributivity. So it leads to bad things. Okay, so you can look at the paper if you want more information on this. Okay, and the second idea is to fluidify the comparisons that involve type variables. And it turns out we can do this very easily by using negation. So thanks to the properties of Boolean algebras, if you have tau and alpha on the left-hand side of a constraint, you can reformulate this constraint by moving the intersected tau from the left-hand side into a negation on the right-hand side. Okay, and now this becomes a bound on alpha, so we know how to solve this, right? We just register the bound and just constrain, propagate the constraint. Okay, and so it just works out naturally, and that's basically the essence of the approach, right? And since all we do here is rewrite constraint to equivalent ones, this means that we always make necessary and sufficient assumptions about the constraint, and so this means we can infer principal types. Okay, so there are many other concepts about MLstruct that I haven't talked about because of lack of time. For example, we actually use normal forms in order to do constraint solving in general. These normal forms are a form of disjunctive normal forms where we reduce redundant constructors and we reduce incompatible constructors. And this is very important for constraint solving to terminate. And subsumption checking, which allows a type signature to be matched against an infer type. Simplification is also very important because you want to make sure that the types you display to users are not a bunch of type variables with lots of bounds, because that's very hard to read and hard to understand. So thankfully, we can simplify types pretty well, thanks to all these assumptions that we made about the lattice of type, meaning that we can reduce types in a pretty aggressive way. And it's natural to ask, what's the complexity of this? Well, as often, it's bad for this kind of type systems. And so it happens to be p-space hard because you can basically encode comparisons between regular languages using unions, intersections, and recursive types, right? So, but in practice, it turns out to work well. We have a lot of tests, several thousand lines of tests of MLstruct code, and it just works out nicely without pathological cases for what we tried. Right, we also have the proofs of these properties, and they are non-trivial. So we are about to release an extended version of the paper with all the proofs. And there's also a web demo that you can try out yourself. And here are some examples, right, where you're defining flat map on option values, and you have the infer types here, as well as the evaluated JavaScript. but I don't think I have time for a demo right now because there are 5 minutes for questions. Yes. Thank you. Yeah.
Questions, maybe we start.
Hi, thanks for a nice talk. I don't think you explicitly mentioned Stephen Dolan's MLsub.
Oh, yeah.
But presumably it looks like this is a conservative extension of MLsub.
Exactly.
Is that
Yeah,
right?
yeah. This language subsumes MLsub, right? Which itself subsumes ML. Yeah, that's right. Thanks for pointing it out.
And what are the main? What's the main delta? Would you say?
What's the main what?
The main delta between MLsub and MLstruct.
Oh, it's definitely union types and intersection types, right? And this notion of
So you have union and intersection constraints in MLsub.
so in MLsub you have union and intersections in the syntax of types, but they are polar. So unions are restricted to positive occurrences, negations to intersections to negative occurrences. So it makes constraint solving completely straightforward, but it doesn't allow you to do this kind of pattern matching type checking where you want to eliminate unions, right? So such as this one.
Right. Okay.
So
Thank you.
actually, this is very significant, right? Mhm.
Hello. It's interesting. I get to do sort of the same exact question that I did for another work. Since you have that 25 is a type, I assume also like foo is a type.
Mm-hmm. You mean the string?
The string foo.
Sure.
So what's really the difference between a function that goes from foo to int and a record with a single field foo that contains an int? Could you just avoid your one field record and represent them with a function from...
Yeah, I see what you mean, but you cannot, not in this language. And that actually relates to the conclusion slide, which I haven't shown, which is that since we merge intersections of function types into single function types, this means we cannot use intersections to encode overloading. So we could not represent records as overloaded function types mapping from record names to values, right? This doesn't work because even if we supported this type without merging it, it would yield ambiguous constraints. So we couldn't have principal types with this. So we need records in this case.
I have a question regarding your nominal tags, because it seems that you only maintain a class name but not the the type argument information.
Exactly,
and I was curious how you can, for example, declare a class int list extends the list of int, which list is list of t is a generic type, and then how can you ensure that if you assume there is a relation between int list to just a list, then how about you falsify the relationship between int list to some list of string, for example, because int and string usually you can regard them as disjoint.
So there's a simple answer and a more complicated answer. The simple answer is that in the core MLstruct type system, everything is structural. So if so int list will have fields that refer to this type argument, and when you expand the type int list or the type list of int, you actually substitute the type argument everywhere, right? So if this type argument is used, it's going to be part of the rest of the type, right? The nominal tag doesn't need to refer to it. The more complicated answer is that in the actual implementation, we also have pseudo fields that remember the value of the type parameter, because we also support more features such as methods, which are not part of the structural type, which allows them to be polymorphic.
So which may seem like the type member in Scala, something.
Yeah, exactly. That's inspired by type members, basically.
Okay, so, thanks for answer.
Mm-hmm.
Thank you for your talk. I'm wondering if you have any idea how your approach scales to multi-inheritance, since it's very useful in OOP. But maybe you may go for trace or mixing to just enable code reuse instead of introducing new subtyping relation. Or
So we're actually adding mixins to MLstruct, which is a language we're developing, and mixins are not associated with types in our approach, so we don't have really a problem here. We also have interfaces which have a type, a nominal type, but you cannot pattern match on them, right? And pattern matching is really the feature for which you need single inheritance. So you can pattern match on classes, but not on interfaces. And you have nominality in both cases anyway. So with interfaces, you have multiple inheritance, right? You just cannot pattern match.
Okay, thank you.
Mm-hmm.
Hi, thanks for the talk. So I have a question. Substitution principle, subtyping, did that hold before? And it doesn't look like it holds now. I'm not sure if it held before you did your algebra.
But what do you mean?
Like
exactly?
Liskov substitute, any property that holds for a subtype should hold for the supertype, right?
Mm-hmm. So structural types should be fine with this. Do you have a counterexample in mind?
Like you seem to have true as a supertype of some other more specific types now. So it doesn't look like you.
True. The singleton type true is.
Yeah. So you had an algebra where now true is a subtype
top,
of.
you mean?
Yeah, like top is a subtype.
Yeah. Okay. So top is, so this is just a way to constrain the lattice of types, basically. So we have unions and intersections as proper type constructors, but some of them are not actually denoting types on their own, individual types. They're actually denoting top. And I don't think this is directly related to the Liskov substitution principle, because it's not about type substitution, right? It's about substitution of behaviors.
Yeah, exactly. So I can prove something about a type that has a constraint that maybe not true about top, right? So, but yeah, okay.
I'm not sure, but maybe we can talk about this.
Thanks.
Offline.
Let's thank Manuel again.
Thank you.